This is Babitha, working as Assistant Professor in the Department of ECE in the of Aeronautical Engineering. In this session, I am going to explain about high frequency equivalent circuit of Mosfet. So, while coming to the contents, just I'll revise the small signal model of the Mosfet. Why? Because if we understand the small signal model, only we can able to draw the high frequency equivalent circuit for the Mosfet. And later on, we'll go with the Mosfet high frequency model. So to see the Mosfet small signal model, here generally Mosfet is a voltage control device. Why it is called as voltage control device means the output current or drain current in the Mosfet is the function of both the gate to source voltage as well as drain to source voltage. So that's why it is called as voltage control device. And one more thing here it is, while constructing the Mosfet, we will use the silicon dioxide layer for the oxidation. So this silicon dioxide layer will offer some 10 power 15 to 10 power 16 ohms of resistance. So because of this much resistance present across the gate, there is no flow of current through gate. So that's why we are not at all considering the gate current or input current in the case of Mosfet. So just we will consider the output current or drain current only, and that is the variation of VGS as well as VDS voltages. So in order to draw the Mosfet small signal model, here I am taking two conditions. First condition is the variation of ID with respect to VGS voltage, and in the second case we will consider the variation of the drain current with respect to drain to source voltages. That is nothing but to see the small signal analysis, we are applying the mixed signal, that is the combination of AC signal as well as the DC signals. That may be the gate to source voltage or drain to source voltage. While providing the two voltages, we are taking the combination of AC as well as DC signals. So to represent DC terms, we will use the capital letters. I have already mentioned this one in the previous sessions. And to represent the small signals, we'll use the small letters. And to represent the mixed signal, that is the combination of AC plus DC, we will represent small letter with capital. Subscript this one will indicate the mixed signal. In this case, the mixed signal is small v, capital Gs. So in order to make the small signal Mosfet with the variation of VGS voltage, that is considering the first case, I am considering the Mosfet with the gate, drain and source terminals. So between gate and source, we are providing DC as well as AC signals. This is your DC signal and this is AC signal. So the combination of both the signals we are providing across the input, and we are maintaining the drain to source voltage as constant value. We are maintaining drain to source voltage as some constant value. So this is VGS voltage. And when we are providing the combination of AC as well as DC signal as gate to source voltage for the Mosfet, we will get the corresponding drain current. That is the combination of DC as well as AC signals which will flow through the drain terminal. So when we provide this particular gate to source voltage, we are getting the corresponding variation in the drain current, so that we can represent graphically here. Here I am indicating ID. Sorry. VGS versus ID signals. So we will get the curve in this. So here the input signal VGS is the combination of AC as well as DC. This is the AC signal and this one is the DC signal. And similarly, we will get across the output the amplified version of this applied input signal. That is also combination of AC as well as DC signals. So the slope of this one will give the parameter called transconductance. So the transconductance GM, we can write it as the variation of ID with respect to the variation of VGS by maintaining VDS as constant value. So here, while drawing the small signal model of the Mosfet circuit, we are getting the parameter GM between the drain and source terminals. So if we draw the small signal equivalent circuit for this gate to source voltage, we will get it as, for that I am considering the three terminals of the FET, that is gate, drain and source terminals. So between gate and source we are not getting any current here. Why? Because I have already mentioned upon the gate we are providing the silicon dioxide layer. It is offering very high resistance. Because of that reason there is no flow of current between the gate and source terminals. So only we are representing the voltage source between the gate and source terminals. And here we will provide the input signal. And between gate and drain terminals we are not getting any voltage as well as any current. So that's why we are not indicating anything between the gate and drain terminals. But between drain and source terminals we are getting the parameter that is GM into VGS. So this is the small signal equivalent circuit of the Mosfet when we vary the gate to source voltage. And similarly, if we take the second case, that is variation of ID with respect to VDS, drain to source voltage. So in this particular case, we will keep gate to source voltage as constant, and in the place of drain to source voltage, we will provide the mixed signal, that is the combination of AC as well as DC voltages. So for that purpose, again, I am considering the FET here with the gate, drain, source terminals. Okay, and here VGS voltage is constant and VDS voltage we are providing DC as well as AC signals. So correspondingly again we will get the drain current, that is the combination of DC as well as AC signals. Okay. So in this particular analysis we will get the curve in this way, that is VDS versus ID. Now we will get like this here. If we take any one particular point on the curve and if we apply the voltage here, and this is the VDS and this is the capital VDS, this input signal we are providing, and correspondingly we will get the drain current as again small id as well as capital ID, sum of both the AC and DC signals, but This is the amplified version of the applied DS voltage. So from this curve we can get the parameter that is G0, again transconductance, but here G0 value is the variation of the drain current with respect to the variation of the drain to source voltage by keeping gate to source voltage as constant. So in this particular kit we got G0 parameter. If we include G0 parameter in the small signal equivalent circuit, we will get it as, for that again consider the gate, drain and source terminals. So between gate and source we are providing VGS voltage, and here we will get it as G0 VDS. Instead of GM VGS, here we are getting G0 VDS. Why? Because we are varying the drain to source voltage and we kept gate to source voltage as constant. And while making this small signal model, if we also consider the channel length modulation into consideration, in that case we will get one extra resistance R now here across the output. That channel length modulation parameter is lambda. If it is not equal to 0 only, we will get R0 resistance in the equivalent circuit. If we are not considering the channel length modulation into effect, means we will not get this R0 resistance in the equivalent circuit. So what is the effect of the channel length modulation in the operation of the Mosfet? Means because of the channel length modulation, the drain current will be increasing in the circuit. Generally, in the Mosfet, while it is operating in the saturation region, if we increase the drain to source voltage, the actual length of the channel will decrease here. Why? Because the number of charge carriers are attracting towards the terminal of the battery. Because of that reason, the number of charge carriers are reducing. Because of the reducing the number of charge carriers, the length of the channel is reducing. So here the channel length is proportional to the resistance of the channel here. So channel length is reducing means the resistance of the channel is also reducing. So once the resistance in the channel is reducing means obviously the current ID will increase in the channel. So because of that reason, due to the channel length modulation, the drain current is increasing in the circuit. And when we are considering that particular effect, that resistance value, we are including in the small signal equivalent model. And if we observe here, in both the cases, we didn't consider any capacitors effect here. Why? Because at low frequencies or at low frequency AC signals, the reactance of the capacitor is very high. So once the reactance of the capacitor is very high means it acts like a high resistance path, so it will not allow the signals here. So we cannot consider the effect of that one here. That is nothing but it will not able to allow the AC signals here. We are going to perform the small signal analysis. If it is not allowing the AC signal, the analysis maybe get different values or not required values. Because of that reason, we are not including the capacitors effect in the small signal model. So this is about the small signal model of the Mosfet. So that same circuit again I am considering here, small signal model of the Mosfet in the low frequency range. So from this small signal model of the Mosfet only, we are going to implement the high frequency equivalent circuit of the Mosfet. So in the case of high frequency model, if the frequency of the signal is increasing means the reactance of the capacitor will decrease. Why? Because the reactance of the capacitor Xc is equal to 1 by 2 pi C. So the reactance of the capacitance is inversely proportional to the applied signal frequency. So if frequency is very high means the reactance value will be decreases here. So that we have to take the capacitor action in the high frequency model of the circuit. So which type of capacitors we need to consider to see the high frequency response of the Mosfet here? Here generally we will be having two capacitors between drain to gate, one capacitor, and between drain between source to gate, one more capacitance will be present in the circuit. At high frequency model, we have to consider drain to gate capacitance as well as source to gate capacitance. And along with this drain to source capacitance as well as drain to gate capacitance, we have to consider two more capacitances. Those are COS and COG. Those are between the gate and source as well as gate and drain. So total 4 capacitors we have to include while drawing the high frequency equivalent circuit of the Mosfet. So along with these 4 capacitances, we will be having 2 more capacitances. Those we can call it as junction capacitances or internal capacitances of the Mosfet. Those are CTS and CTD capacitances. Those are between the source and substrate. CTD is nothing but between source and drain, and CTS is nothing but between source and substrate here. But generally, if we take the Mosfet, it is having 4 terminals, but in the operation point of view, we are interconnecting the substrate terminal with the source terminal. When we are interconnecting the substrate terminal with the source terminal means we can remove this particular CTS capacitance. So these 4 capacitances plus one internal capacitance, that is CTD, is included in the high frequency equivalent circuit. So overall we can say to see the high frequency equivalent circuit of the Mosfet, we need to include CGS capacitance between source and gate, and CDG capacitance between gate and drain, and CTS capacitance between substrate and source, and COS capacitance between the gate and source, and COG capacitance between the source and gate. So these 5 capacitors we need to include in the small signal equivalent circuit of the Mosfet to make it as high frequency equivalent circuit. So after including all the capacitances, this is the high frequency equivalent circuit of the Mosfet. So to draw this, first of all we have to consider the small signal model and we have to include all the capacitors. These capacitors are nothing but coupling capacitors, bypass capacitor, as well as internal capacitors. These 5 capacitors are nothing but these coupling, bypass, as well as internal capacitances. So here the CGS capacitance is connected between the gate and source terminal, and as well as COS is connected between the gate and source, and COD is connected between the gate and substrate, and CGD is connected between the drain and substrate, and CTD is connected between the drain and substrate. So for simplicity and in order to analyze this particular circuit, I have including CGS as well as COS capacitors lumped together with the CGD capacitor here. Okay, this COS as well as CGS capacitances are lumped together and those are included in the CGD capacitance here. And this CTD capacitance is very high compared to the COD capacitance, so that we can neglect the effect of this particular capacitance hereby because it is connected to the parallel So if it is high means it will grounded the total applied signal here. So there is no signal will appear across the. Okay. So the above circuit is modified to calculate the short circuit current gain of MOSFET here. So the overall capacitances, that is COS between the gate and source and COD between gate and drain, are lumped together in the gate to drain capacitance. I have mentioned this. And the capacitance between the drain and substrate, that is CTD, is very large, so that we can neglect it, that particular capacitance. So equivalent, if we draw the equivalent circuit after applying the short circuit at the output port, and if we apply the input signal across the input port. So after modification of all these capacitances and after applying the input signal and short circuiting the output terminals, we will get the equivalent circuit as in this way. So here VG, we are applying the input voltage and the output terminals are shorted and all the capacitors are included across the gate and drain terminals. So this is the high frequency equivalent circuit of the MOSFET. And this is the simplified version of the equivalent circuit of the MOSFET in order to determine the FT, that is transition frequency. So here to find the short circuit current gain, again the same circuit what is there in this slide I am considering in the next slide. From this circuit, if we find the input current, that is IN, that is equal to input voltage, that is between here gate to source VGS into J omega, that is reactance of the capacitor, into two capacitors which are present here, CGS as well as CGD, that is CGS plus CGD. So this is the overall input current which is flowing in the input side of the equivalent circuit. And similarly, if you find the output current I out, that is the GM VGS here. So the current gain AI is the ratio of the output current I out by input current I. If we see that ratio, we will get it as GM by J omega CGS plus CGD. So suppose here in this particular equation, suppose if omega is equal to 0. If omega is equal to 0 is nothing but the reactance of the capacitor is 0. In that case, we will get the current gain as infinity. In that particular case, we will get the short circuit current gain as infinity. When omega is equal to 0, we will get the short circuit current gain as infinity. And what is meant by transition frequency here? So transition frequency FT is nothing but this is the short circuit current gain at particular short circuit current gain, that when we have to take it as 1, short circuit current gain is 1. At that gain as 1, how much frequency it is there on the curve, that indicates the transition frequency here. So the transition frequency FT equal to GM by 2 pi into CGS plus CGD. So now here, if we make in the IN equation omega is equal to 0. In the IN equation, if we make omega equal to 0, the short circuit current gain, we will get it as infinity. Why it is get it as infinity means we are not considering the effect of leakage current. Why? Because the leakage current is very small, that is due to the minority charge carriers. So we have to neglect that leakage current. Once we neglect the leakage current, we will get the gain as infinity here. And from the transition frequency, we can also find the figure of merit of the circuit. So the figure of merit of the MOSFET is the transition frequency FT. So this transition frequency FT specifies the maximum usable frequency of the transistor. Okay, so we can define it as is the frequency at which the short circuit current gain becomes unity. Okay, wherever the short circuit current gain AI is equal to 1, that particular frequency we can call it as transition frequency. Okay, generally in the case of MOSFET, we will use the polysilicon dioxide layer as the gate material. So overlap capacitances, that is COD and COS, get reduced here because of this silicon dioxide layer. So because of that reduction of the capacitance will improve the high frequency response here. In the case of MOSFET, the transition frequency ranges from 100 megahertz to some gigahertz range. So if we compare the MOSFET FT, that is transition frequency, with the BJT, the transconductance of BJT is directly proportional to its bias current. But in the case of MOSFET, it is directly proportional to the square root of the bias current. That is the basic difference in the BJT as well as in the MOSFET. And also in the case of BJT, the transconductance is independent of the physical size as well as geometry of the device. But in the case of MOSFET, the transconductance depends on the physical size as well as geometry of the MOSFET. So even though the transconductance is very less in the MOSFET compared to the BJT, we are utilizing in many applications. Why? Because even though it is having small transconductance, it is having very less size and the cost is also very less, and it provides the high frequency response compared to the BJT amplifiers. And we can easily implement this MOSFET on the integrated circuits. Because of all these advantages, mostly we'll prefer the MOSFETs in order to fabricate the ICs instead of BJTs here. And also it will provide very high input impedance compared to the BJT here. Even though both the BJT as well as MOSFET are useful for switching application as well as amplification application, but because of these reasons, mostly we'll prefer the MOSFET for the fabrication techniques. And we will see one problem related to this high frequency model. So the given problem is, for a MOSFET, CGS is equal to 4 picofarads and CGD equal to 1 picofarad, and the transition frequency is 63.66 megahertz. Calculate the value of transconductance, that is nothing but GM we need to calculate. So from the previous analysis, we calculated the GM parameter, that is 2 pi ft into CGS plus CGD. So here all the values are given. Substitute 2 pi into ft is 63.66 into 10 power 6 into CGS is 4 plus CGD is 1 into 10 power minus 12. Why? Because it is in picofarads. If we simplify, we will get it as 2 millisiemens. The transconductance we will measure in Siemens, so we got it as 2 millisiemens here. So from this high frequency model and how the each and every capacitors will affect the high frequency response of the circuit, we'll see now. Generally, I am considering one frequency response, that is frequency versus gain. So this is the frequency response curve we will get. How we will get this frequency response curve means we have to fix one input voltage as a constant value, and later on we have to vary the frequency of this particular input voltage with the different frequencies, that is 10 Hz, 20 Hz, 100 Hz, 1 kilohertz. So we have to vary the different frequency ranges. So once we vary the different frequency range of the signal, we will get different output voltages. So from this output voltages, we can calculate the gain here. And this gain we have to represent in dBs. So if we draw the curve that is between frequency versus gain, we will get it as like this. For different frequencies, how much gain we are getting. And upon this curve, I am drawing one line. So what is this line indicates means, suppose this is the maximum gain we are getting from the amplifier circuit, that is AV, almost it is 1. So where the gain is falling 70.7% of its maximum value. Okay, that value we are considering here. If it is 1 means we will get it as 0.707. So at 0.707, I am drawing one line parallel to the frequency axis. And where this line is cutting the frequency response curve, the 2 points I am considering here. So this point I am taking here it as lower cutoff frequency, and this point I am taking here it as higher cutoff frequency FH. So if we find the bandwidth of any particular Mosfet amplifier, we have to take the difference of this upper cutoff frequency minus lower cutoff frequency. So this one will give the bandwidth of Mosfet amplifier here. So that indicates the frequency range of the signal. That particular frequency range of signals are allowable to that particular amplifier here. So generally if we take the ideal case, we will get the frequency response curve in this way. That is nothing but for all the frequency ranges, we will get the constant gain in the ideal case. But in the practical case, only for the mid frequency range only we will get the constant gain. And gain is falling down during the low frequency ranges as well as above the high frequency ranges. Why we are not getting the stable or constant voltage gain for all the frequency ranges means that is due to the effect of different capacitances in the circuit. So suppose if we take the low frequency range as well as mid frequency range and high frequency range. So what are the capacitances are affecting in these particular frequency ranges, and because of that effect how this gain is increasing or reducing, we will see now. So for that, I am considering first coupling capacitors. So in the case of Mosfet, the coupling capacitors are the input capacitors as well as source capacitance. So in order to see the effect of this one, again I am taking the reactance of the capacitor, that is 1 by 2 by Fc. So if we take mid frequency signal or high frequency signal. So if we take the mid frequency or high frequency signal, the reactance of the capacitor is very less here. So if the reactance of the capacitor is very less means capacitor acts like a short circuit. So once the capacitor acts like a short circuit means it can able to allow the total applied signal to the circuit. The input coupling capacitor function is to couple the input signal to your amplifier circuit. So once the capacitor acts like a short circuit means the overall input voltage, how much we are applying for the amplifier, it is coupled to the gate terminal of the Mosfet. So once if we are applying the maximum input voltage means ultimately at the output of the amplifier we will get the maximum output voltage. So once we get the maximum output voltage means there is a gain increment in the circuit. Okay, so but here the capacitor is short circuiting here means the input voltage is coupled to the circuit and we are getting it as AV. And if we take the low frequency signals, okay, gain is increasing here. In this case, gain is increasing. But if you take the low frequency range, the reactance of the capacitor will increase here. So once the reactance of the capacitor is increasing means the capacitor will allow only few amount of the voltage whatever we are applying to the circuit. So only the applied voltage is only very less means the output voltage is decreases. So once the output voltage is decreasing means the gain is also decreasing here. So that's why at low frequency range, the gain is reducing here. That's why we show in the frequency response curve, gain is reducing in the low frequency range. And similarly, if we take the effect of the bypass capacitors, that is CS. If you take the bypass capacitor effect, here also at mid and high frequency ranges, the reactance is very less, so the output voltage is very high here, so that gain is increasing here. But at low frequencies, again the reactance of the bypass capacitor is increases and the output voltage is decreases. Why the output voltage is decreasing here means this coupling capacitor acts like a parallel combination to the coupling resistor which is present in the source terminal. So the source resistance as well as source capacitor acts like a parallel combination. It forms like a impedance circuit so that the overall voltage is reducing. And if the overall voltage is reducing means the gain is also reducing. So in the case of low frequency range, because of coupling capacitors as well as bypass capacitors, the gain value is reducing here. And one more capacitors here we are having are internal capacitors. So these internal capacitors are present between the gate and drain terminals, that is CDG, and between gate and source terminals, that is CGS. So because of this internal capacitors effect, there is a reduction of gain at the high frequency range. Why? Because this CGS at high frequency ranges, the reactance of the capacitor is decreasing here. So once the reactance of the capacitor is decreasing means these internal capacitances, actually this internal capacitance is depends upon the silicon dioxide layer which is present across the gate terminal. So this capacitance value will decrease the overall gain of the circuit because of the high resistance which is present in the silicon dioxide layer across gate terminal. And at high frequency range, gain is reducing here. But if we take the mid frequency range, there is no effect of capacitors here. Why? Because in the mid frequency range we are not considering the effect of any capacitor, so that's why we are getting the constant voltage gain here. So finally we can say, by using the coupling capacitors Cin and Cs as well as bypass capacitors Cs, there is a reduction of gain in the low frequency range of signals. And because of the internal capacitances CGS and CGD, there is a reduction of gain in the high frequency range of signals. But at mid frequency range, we will get the constant gain. So it depends upon our applications, and we have to operate our amplifier in the mid frequency range in order to get constant current gain. So here we are assuming here it is from the practical amplifier also we need to get constant gain, but because of all the capacitors effect we are not getting the constant gain for all the frequency ranges. And this frequency response is not similar for all the types of amplifiers. In the common source amplifier it may be different, and in the common gate it different, and in the common drain amplifiers it will be different, and also at different frequency ranges. And because of different coupling schemes also, this frequency response will change here. And if you take the direct coupling of the amplifiers, directly we will connect output of one circuit to the input of the second circuit. So in that case, there is no effect of the capacitors we may get in this particular type of response only. But if we take the RC coupling means we will use the resistor and one more extra capacitor. So because of the impact of that particular capacitor, there is a change in the frequency response. And similarly, if we take the transformer coupled amplifiers, in that case, because of the windings of the transformer, there is a change in the frequency response. If the windings is changing, means the resistance values in the circuit will changes, so that the frequency response will also change here. So in this way, because of the different capacitors action, the frequency response of the circuit will change, especially at high frequency range. Here we are discussing about the high frequency response of the Mosfet. So in that case, the gain will be reduces here. In the high frequency response of the Mosfet, the gain is reducing due to the gate to source capacitors as well as gate to drain capacitor here. So this is the session related to the high frequency equivalent circuit and its frequency response in the case of Mosfet. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.